Welcome to the debate. Today we're walking right up to the edge of the abyss. Literally. We are revisiting the black hole information paradox. You know, that 50-year-old standoff between general relativity, which says information falls into a singularity and just vanishes, and quantum mechanics, which insists that information absolutely must be preserved.
But we aren't just rehashing the same old problem today. We're looking at a specific, highly technical resolution found in the Gibsonian event horizon formalism.
Right. And I have to say, this formalism is bold. It basically asks us to throw out the smooth geometry of Einstein, the very fabric of space-time as we've always known it, and replace it with a discrete lattice, just a grid of S units exchanging tokens. I mean, it sounds a bit like we're trying to turn the universe into a Minecraft server. Well, it is a paradigm shift, certainly, but the core proposition here is that the universe is not a smooth continuum. It's a discrete lattice, and what we traditionally call an event horizon is not a geometric breakdown or a hole in space. It's actually a token saturation zone.
Right, and that's exactly where I start getting skeptical. Because usually when you try to discretize gravity, when you try to turn smooth space into a checkerboard, you lose the beautiful thermodynamic properties of black holes that we've spent decades verifying. You lose Hawking radiation, you lose entropy. So the central question for our debate today is this: can a computational congestion zone, which is what this theory literally calls a black hole, actually reproduce the physics we see? Or is it just, a mathematical toy model?
And that is exactly the question we need to answer. I represent the position that this discrete token saturation is in fact the more physical description. My argument is that black holes are regions of maximum computational throughput. They aren't where physics breaks down. They're where the computer is simply working the hardest.
And I'm here to kick the tires on that. I want to know how a discrete grid explains heat, radiation, and time dilation without just artificially asserting them. Because frankly, if you can't recover the smooth macroscopic world from this blocky microscopic one, the theory is dead on arrival.
Fair enough. Let's start with the foundational substrate described in the material. We are assuming reality is a graph, specifically a tetrahedral lattice of S units. Evolution happens in discrete steps, or Planck ticks, via token exchange. Now, the crucial concept here is the capacity axiom,
which, translated into plain English, is essentially a bandwidth limit.
Precisely. Every point in space, every single S unit, has a maximum token capacity, let's call it Tmax. This follows directly from the full complement rule in the source material, which dictates that a particle only advances after receiving a full set of tokens from its neighbors. So there is a strict update budget. You simply cannot pile infinite energy into a finite point.
Okay, I follow the setup. You have a grid, and the grid has a hard speed limit. But here's the problem with that. In standard traffic, when a road hits 100% capacity, traffic stops entirely. It becomes a parking lot. This formalism claims that an event horizon is a region where the token occupancy hits Tmax. It's a token storm. But if it's fully saturated, surely the region must freeze?
I see why you might think that. And that is actually the standard intuition for a grid. If the bucket is full, you can't put more water in, so the flow stops. But let me give you a different perspective, drawn directly from the no-freeze theorem derived in the papers. The definition of a horizon here is that the token count, T, equals Tmax for all sites in the region. But look at the actual update rule. Y sub n plus 1 equals Y sub n plus the token count, T, times the function f.
Okay, hold on. Let's decode the math for a second for the sake of clarity. You're saying the update rule, the exact mechanism that drives time forward, is dependent on that token count, T?
Exactly. As long as T is non-zero, and here it's not just non-zero, it's maximal, it's hitting the absolute ceiling, the update term remains non-zero.
So the state variable y actually continues to change?
Y sub n plus 1 is not equal to y sub n. The region is dynamically active. It resembles a CPU running at 100% utilization. A computer that is fully maxed out hasn't crashed. It is just too busy to accept new input from the keyboard.
I'm sorry, but I just don't buy that entirely yet. Because if it's too busy to talk to the outside world, isn't that functionally identical to being frozen from the perspective of an outside observer? I mean, if I shout into the hole and it can't process my sound because it's too busy, that looks an awful lot like the information is just gone.
That's a compelling argument. But you have to consider the technical distinction between being externally opaque and internally active. The material defines the outward transfer flux as phi out. At saturation, all the ports or channels of these S units are completely committed to internal exchange just to handle that massive token load. So phi out naturally goes to 0. It acts as a bandwidth firewall. But phi internal is strictly greater than 0.
So the no-freeze theorem essentially says the lights are on, the machinery is spinning maximally, but the door is jammed shut because there's simply too much happening inside.
That is the discrete horizon theorem in a nutshell. The supposed information loss is just a category error, because we assumed a geometric singularity, a point where physics flat out stops. Here, physics never stops. It just gets really, really dense. The state space, omega, is not reduced at all.
Okay, I can accept that as a logical possibility. It's a busy signal rather than a disconnected line. But let's pivot to thermodynamics, because you can't just say it's busy and solve the paradox. Black holes have entropy, massive amounts of entropy, and in general relativity, that entropy is famously proportional to the area of the horizon. How does a discrete graph reproduce that? Because historically, discrete models really struggle to get the numbers to match the Bekenstein-Hawking formula.
This is where the model is frankly surprisingly elegant. In this framework, entropy is defined traditionally as state distinguishability. S equals the sum of the log of omega.
Right, standard Boltzmann entropy, the number of ways you can rearrange the furniture without changing the room.
Correct. Now recall that our horizon is strictly defined by saturation. You have the maximum possible number of tokens dancing around on these lattice sites. When you maximize the token count, you naturally maximize the number of reachable states, or microstates, at that specific location.
I see, because an empty grid site has only one state. It's empty. A partially full one has a few distinct arrangements, but a completely full one has the combinatorial maximum.
Exactly. Therefore, horizons naturally correspond to entropy maxima. You don't need to invoke infinite geometric curvature to explain why there's so much hidden information. The information is hidden in the sheer multiplicity of the token configurations required to maintain that state of saturation.
Okay, that's a consistent internal logic. It maps area to the number of lattice sites and curvature to token density. But now we have to address the elephant in the room, or rather, the radiation in the room.
Hawking radiation.
Yes, Hawking radiation. This is the absolute gold standard. If your theory can't do this, it's game over. In semi-classical gravity, radiation comes from vacuum fluctuations in a smooth continuum particle, pairs separating right at the horizon. You have a discrete lattice. You don't even have a continuum vacuum. How on earth does a token storm radiate?
This is actually my favorite part of the material. It's called the decongestion mechanism. And you're right, it is not pair creation in the traditional sense. It is a boundary fluctuation.
Walk me through that.
Imagine the boundary of this saturated region. It's a wall of maxed out nodes. But the entire lattice is subject to local stochasticity, basically noise, which is modeled mathematically as a discrete Ornstein-Uhlenbeck process.
Let's quickly clarify that for anyone listening. An Ornstein-Uhlenbeck process is basically mean-reverting noise. Like a rubber band, it fluctuates, but it always wants to snap back to the average.
Exactly. So even though the region is saturated on average, there are random fluctuations. Occasionally, a site at the very boundary momentarily dips below saturation, a change in T of -n.
A dip in traffic, a momentary gap in the shield.
Precisely, a tiny hole in the saturation wall. This opens a one-tick outward channel. Because the pressure is lower for just a split second, a packet can escape.
But random dips, that sounds like noise. Pure white noise. Hawking radiation has a very specific thermal spectrum. It follows a perfect black body curve. Does your traffic dip actually look thermal? Because if it just looks like random static, you haven't derived Hawking radiation.
Oh, it does look thermal. And this relies on large deviation theory. If you look at the statistics of these fluctuations, the probability of a dip of size e follows an exponential tail. The probability of e is proportional to the exponential of -e over theta.
That is the Boltzmann factor. That's a literal definition of a thermal distribution.
It is. The temperature, theta, here is controlled by the gradient of the token potential right at the boundary.
The token potential gradient, that sounds exactly like the discrete analog of surface gravity.
It is exactly that. In general relativity, temperature is proportional to surface gravity, which measures how steep the gravity is at the hole. Here, theta is proportional to the steepness of the change in token density at the edge, so hotter horizons are simply those with steeper token gradients.
That is surprisingly robust. You get the exponential tail just from the pure statistics of discrete fluctuations. But wait, let me come at this from a different angle. If the spectrum is genuinely thermal, it's completely random. If it's random, it carries zero information. And if it carries no information, you haven't solved the paradox at all. You've just reinvented a discrete way to destroy information. You've made a digital shredder instead of an analog one.
I completely see why you think that, but let me give you the Gibsonian twist. This is the subtle part of the paper. While the spectrum looks thermal in its magnitude, the one-point statistics, the actual emissions are not independent.
Explain what you mean by not independent.
The boundary fluctuations, those momentary dips, are conditioned on the interior storm microstate. Let's call it state X. The storm inside determines exactly when and where the boundary fluctuates. Therefore, the covariance between an emission right now and an emission later on is strictly not zero.
So there are subtle correlations hidden in the timing or the sequence of the escaping packets?
Precisely. Think of it like this. If I send you a message encrypted with a really good one-time pad, it looks like pure random noise to anyone intercepting it. It has all the statistical properties of thermal noise, but it isn't noise. It's fully deterministic based on the encryption key. Here, the key is the internal state of the black hole. The radiation carries the information away in the incredibly complex smear of these correlations.
So the randomness is actually encrypted data from the interior?
Yes, it entirely prevents information destruction because the system remains unitary. The exterior universe simply reads the output of the interior's processing, just very, very slowly and in a highly scrambled format.
But let's press on that mechanism for a second. You're saying the interior storm decides when the gap opens.
Well, not decides with agency, of course, but determines via strict causality. The lattice is fundamentally deterministic. The specific configuration of tokens inside which represents the physical matter that originally fell in, creates the highly specific pressure conditions at the boundary. So a specific book falling in creates a specific, unique pattern of boundary fluctuations much later.
Meaning, if I could practically collect all the Hawking radiation and had a godlike supercomputer to reverse the correlations, I could actually read the book.
In principle, yes. The information is strictly conserved.
I have to admit, that beautifully covers the how. It's an information leak disguised perfectly as thermal noise. But let's talk about the how long. Does this thing actually evaporate? Because Hawking predicted a black hole's lifetime scales with its mass cubed. A big black hole lives a very, very long time. Does your model match that scaling?
It can, but it also offers a really fascinating deviation. The source material derives an evaporation law based on the boundary softening, and it turns out there are two microphysical regimes, which are controlled by a parameter they call the knob, denoted as Q.
A knob? You mean a tunable variable depending on the underlying lattice rules?
Yes. It essentially depends on how clean the routing is at the boundary. Regime A is the classical fixed point, where Q equals 8. This corresponds to high routing suppression, meaning it's really hard for tokens to find a way out. In this specific regime, the math lands exactly on Hawking's mass-cubed scaling.
So if the lattice is sticky or highly congested, you recover standard continuous physics. That's a vital sanity check. It basically means Einstein's gravity is just the limit where the discrete grid is highly inefficient.
Correct. But there is also regime B, the Gibsonian deviation, where Q equals 1. This represents much cleaner routing, where if a gap opens, the token almost certainly escapes without scattering back.
And what happens to the lifetime in regime B?
It burns much faster. The lifetime scales as mass to the power of 2/3.
Whoa, mass cubed versus mass to the 2/3. That is a massive difference. I mean, for a stellar mass black hole, mass cubed is roughly 10 to the 67 years. Mass to the 2/3 would be, well, drastically shorter. That implies that if we ever observed an evaporating primordial black hole, we could distinguish this discrete model from standard semi-classical gravity just by watching a clock.
Exactly. It makes the theory entirely falsifiable. It's not just abstract metaphysics, it's a hard prediction about evaporation rates. If we found a primordial black hole exploding today, its mass to temperature ratio would tell us immediately if we live in a Q equals 8 or a Q equals 1 universe.
That is huge, because usually these quantum gravity theories hide safely behind the Planck scale, where we can never physically test them. This one is really sticking its neck out on the macroscopic evaporation rate.
And there is one more highly testable prediction in the paper: species-selective emission.
I saw that in the notes. This is about different fundamental types of particles behaving differently.
Yes. In this discrete view, an excitation isn't just a wave. It has a literal token cost. To emit a particle, you need a budget of n tokens. But you also need a clear escape path through the network. The material mathematically suggests that weakly interacting species, like neutrinos perhaps, would have a much lower interaction cross-section with the boundary network itself.
So they escape the congestion easier.
Much easier. They effectively probe a completely different temperature than strongly interacting particles. The theory predicts that the Hawking radiation spectrum shouldn't be perfectly universal. Different species should show slightly different effective temperatures.
That is a smoking gun. Standard Hawking radiation says a black hole radiates like a mathematically perfect black body. It doesn't care what the particle is, only its spin and mass. You're saying the grid actively discriminates.
The grid discriminates based on routing complexity. Weakly interacting modes preferentially carry the energy flux, and importantly, the information content.
You know, I started this conversation thinking, okay, just another grid theory trying to crudely approximate Einstein. But this isn't just an approximation. It's a distinctly different physical claim. It's saying that if you look closely enough, the smooth geometry of gravity is actually an illusion. And the underlying computational machinery has quirks, like this species discrimination, that we should be able to physically see.
I agree completely. It posits that space-time itself is just an emergent output of these local update rules.
I'm still stuck on the implications of the no-freeze theorem, though. I want to circle back just one last time. I challenged you on whether a saturated region is truly active. You convinced me that mathematically the update rule holds. But physically, what does it truly mean for a region to be opaque but active? Can we get a metaphor that lands this for the non-physicist?
Sure. Think of it like a dark room filled with people having an incredibly frantic conversation. From the outside, you see absolutely no light leaving the room. It's pitch black, opaque. But inside, the state is evolving rapidly. The conversation, the actual information processing, never stops. Standard general relativity assumes that because the room looks dark from the outside, time itself must have stopped inside. The discrete token saturation model says, no, we just can't hear them because the walls are too thick.
And the walls are literally made of bandwidth constraints.
Precisely. The horizon is a bandwidth firewall. It's not an event horizon in the geometric sense at all. It's an information horizon.
Which brings me to a rather wild thought. If the horizon is just a bandwidth cap, does that mean you could technically saturate space without any mass or gravity just by pumping enough raw information into one specific spot?
Theoretically, yes. If you concentrate enough computational density into a small enough volume of the lattice, you trigger the exact saturation condition. Gravity is just the macroscopic symptom of that saturation.
That flips the whole script on its head. Gravity doesn't cause the black hole. The extreme information density causes the black hole, and gravity is just what that bottleneck looks like from far away.
Precisely. It's a pure information-first approach to cosmology.
I have to ask about the evaporation law again before we wrap up. You mentioned the knob parameter. Is there any clear indication in the source material which regime, the classical or the Gibsonian, is the real one, or is it just left open?
The material presents it as a parameter family, but it explicitly notes that regime B is the cleaner phase boundary. If black holes are truly just computational phase changes, one might theoretically expect the cleaner routing. The fact that standard continuous physics demands Q equals 8 might actually just be a sign that standard physics is only looking at the congestion-dominant limit of a much more general discrete mechanics.
That's a very polite way of saying standard physics might be a special, slightly inaccurate case of this broader theory. Just like Newton was a special case of Einstein.
Well, I would frame it differently. I would say standard physics flawlessly captures the macroscopic fixed point, while this theory finally exposes the microphysics underneath it all.
And the simulation results mentioned in the papers, they actually back this up?
They did. The boundary microsimulation generated packet energies that followed that exponential thermal tail perfectly. And the autocorrelation of the power signal was definitively non-zero. It decayed, sure, but it was there. That confirms the mechanism works dynamically in a computer simulation, not just on a chalkboard.
It proves the mechanism is logically self-consistent, at the very least.
Which is more than we can say for the standard singularity, which is mathematically inconsistent by its very definition.
Touché. A singularity really is just the math screaming, I give up.
So, having gone through all this, where do you land? Do we live in a smooth continuum that inevitably breaks down, or on a tetrahedral lattice that just gets a bit too busy?
I have to say, the closed logical loop here is incredibly satisfying. The paradox in standard physics arises because you have two deeply conflicting absolutes: the event horizon as an absolute point of no return, and the absolute unitarity of quantum mechanics. This model resolves it by simply softening the first absolute. The horizon isn't a geometric point of no return, it's just a computational limit.
And limits can be safely reached without breaking the machine.
Right. It transforms the permanent loss of information into a mere latency of information. It's still there. It's just stuck in the buffer. Now, I'm not 100% sold on the tetrahedral graph being the literal final answer for the universe's shape. I'm still an Einstein loyalist at heart, but as a rigorous resolution to the paradox, it holds water. It solves the problem without resorting to magic.
And it does so without inventing new parallel universes, or holography, or complex wormholes. It just asks us to take the simple concept of finite bandwidth seriously.
It brings physics back to something almost tangible. Traffic, bandwidth, processing power. It completely demystifies the black hole. It makes it a physical, functioning object, not a mythical monster. And honestly, the idea that a black hole is just a cosmic computer that's lagging because it has too many Chrome tabs open, I can definitely relate to that.
That is exactly the goal. Black holes are not the end of physics. They are simply extreme computational regimes, maximal token throughput regions.
And if we can ever successfully measure that spectral deviation, that tiny difference in temperature between a photon and a neutrino coming from a black hole, we'll know for sure.
We will indeed.
Until then, I suppose we just have to keep updating our own internal states.
Well put. We hope this deep dive helped illuminate how a discrete perspective can offer a genuinely rigorous path forward through one of the densest problems in all of physics.
It's certainly given me a lot to process.
Thank you for listening. Consider if your own spacetime is just an emergent output of local update rules. Good night from the debate.